So those first few questions probably not really going to appear in their form like that on the A level, although you do need to know it. Now we move into what I'm calling gases and two, moles and gases. This is based around the ideal gas law as well as molar volume, and this is very definitely something that is on the A level specifications. So which following amounts of gas will have the greatest volume at STP? Well, we know that the molar volume at STP is 22.4 litres. Any gas, 1 mole of any gas occupies 22.4 litres at STP. So let's look at what we're given here. Give ourselves a little bit of space. 7 moles of Cl2, well therefore the volume of 7 moles of Cl2 will be the 7 moles that were given times the 22.4 litres that 1 mole of any gas occupies. So 7 moles of Cl2 occupies 7 times 22.4, 156.8 litres. 22 grams of He, well of course as soon as you see grams of any pure substance you convert it to moles. Molar mass of helium is 4, 22 divided by 4, 5.5 moles. What's the volume of 5.5 moles of any gas, in this case helium at STP? 5.5 times 22.4 or 123.2 litres. Another way of expressing things, 2.01 times 10 to the 24 atoms of neon. Well, let's see. Atoms, in this case of neon, 1 mole of neon is 6.02 times 10 to the 23 atoms of neon. So we got this many atoms of neon. How many moles is it going to be? 2.01 times 10 to the 24 divided by 6.02 times 10 to the 23, which is 3.34. And of course, 1 mole of any gas is 22.4 litres at STP, so 3.34 moles of neon at STP, 3.34 times 22.4, or in other words, 74.8 litres. And finally, 112 litres of methane gas has a volume of 112 litres. So which one has the greatest volume at STP? The 7 moles of Cl2. So a kind of cute one. Sample of gas occupies volume of 5.7 litres, particular temperature pressure, 4 moles gas added, new volume 11 litres, same temperature pressure. How many moles of gas were present initially? Well, this all revolves around the Avogadro hypothesis that the volume of any gas is proportional to the number of moles at a given temperature and pressure. Well, how shall we apply this? Well, we know that 5.7 litres contains X moles. We know that when we add 4 moles of gas, we get up to a volume of 11 litres. So in other words, adding that 4 moles took us from 5.7 up to 11.0. In other words, that 4 moles of gas that we added has a volume of 5.3. Okay, so 4 moles has a volume of 5.3. We're interested in how many moles have a volume of 5.7. So we just set up a little ratio. X occupies 5.7, 4 occupies 5.3, multiply it out, and X is 4.3 moles. Based on the idea, all going back to Avogadro's hypothesis. So a fun one, just to see where it all comes from. The ideal gas law, PV equals nRT. So let's go through the ABC of gas laws. Avogadro's hypothesis is the A. Avogadro said that the volume is proportional to the number of moles. There's volume here, there's number of moles here, assuming that temperature and pressure are constant. So that's Avogadro, very definitely part of the ideal gas law. Boyle, the B of the gas laws. Volume is proportional to 1 over pressure. Well, if we multiply this up, we would see that volume times pressure is proportional to something. There's volume times pressure proportional to nRT, so assuming temperature is constant, and the given moles of your gas sample are constant. The C is Charles, volume proportional to temperature. There's volume, there's temperature, assuming pressure and moles are constant. Skipping now a couple of letters, we get to G for Gay-Lussac. Gay-Lussac, pressure and temperature proportional. There's pressure, there's temperature, assuming volume moles constant. So the A, B, C, G are all in the gas law. So what's Graham's law? Well, Graham's law that you might touch on in chemistry, you certainly touch on in physics, relates to the velocity of gas and the molar mass. Essentially, the velocity of a given gas at a given temperature is proportional to 1 over the square root of its molar mass. Big R, molecules move more slowly. So obviously very important law, but nowhere do we see velocity, molar mass directly in the ideal gas law. So the answer here is Graham's law is not part of the ideal gas law. Fairly straightforward PV equals nRT question. We want to know the volume, we got the temperature, we got the pressure, and we've got grams of a gas, so we can easily turn that to moles. So let's go through what we know. Pressure, 69.9 kilopascals. That's a fine unit to use, as long as we use the right value of R. Volume, don't know. Grams, 25.4 grams. Well, that's of nitrogen gas. Nitrogen gas is N2. Atomic mass of nitrogen is 14, so we'll just divide 25.4 by 28 grams per mole, and we get that's 0.907 moles. Temperature, of course, never ever use anything but Kelvin, so we'll add 273 to that to get 298. Plop everything in. Now the value of R, 8.314 cubic meters pascals per mole Kelvin. That's our moles, that's our Kelvin. So we'll obviously have to use pascals here. So this will become 69,900. Pop all that in, and that gives us our volume as 0.0322 cubic meters. And I believe the actual answer was in liters or cubic decimeters. We just multiply that by 1,000 to go from cubic meters to cubic decimeters. And so we get 32.2 liters, 32.2 cubic decimeters. Volume, 71.9 mils, water vapor, that's the pressure, that's the temperature. How many grams of water vapor are there? Well, PV equals nRT. See what we got. Pressure, 10.4 atmospheres. Volume, let's use liters, so 0.0919 liters. Moles, we don't know. Temperature, 465 plus 273 Kelvin. And if I'm using atmospheres and liters, R is 0.0821. Pop all that in your calculator, and N is 0.01234 moles. And of course, water is this particular vapor. And how many grams does that weigh? Well, we just multiply it by 18 grams per mole to get the final answer, 0.222 grams. This one is nice, and I believe goes past the immediate A level, but there's no reason you can't answer it. Mixture of nitrogen, oxygen, argon at STP, occupy a 5-liter container. If the mole fractions of nitrogen, argon, 0.55, 0.25, how many molecules of O2 are present in the container? Well, first of all, STP, we know that 1 mole of any gas or any mixture of gases, 22.4 liters at STP. So we've got 5 liters, so therefore we have 0.223 moles of gas. Okay. Now we know that 0.55 fraction of that is nitrogen, 0.25 of that is argon. We're interested in oxygen. So the mole fraction of oxygen is 1 minus the 0.55 minus 0.25. So 0.2 of these gas particles, gas molecules in there are going to be oxygen. So therefore the moles of oxygen is going to be 0.2 times 0.223 or 0.0446 moles. Now that's the toughest part about the whole thing, just stepping through it. First of all, we know all about STP, so we can figure out the total number of moles. Once we know the total number of moles, we can figure out what fraction of those are oxygen and then apply that. Then of course, once we've got moles, moles converts to molecules quite simply by molecules is moles times 6.02 times 10 to the 23. So 0.0446 moles times 6.02 times 10 to the 23 gives us 2.68 times 10 to the 22 molecules of O2. So an application of molar volume and then just thinking your way through it. Density of oxygen gas, grams per litre. Now remember, from the ideal gas law, PV equals nRT, you can replace N moles by grams over molar mass and then rearrange that as we need. In this particular case, we want density, which is the grams over volume, is P times the molar mass divided by RT. The derivation of that relatively straightforward and is of course in the movies. So let's see what we got. Pressure 0.061 bar, temperature 298. I'm just going to automatically turn that now. Molar mass of oxygen is 32 grams per mole. Pop everything in here. So the density, grams over volume. There's the pressure in bar, 32 grams per mole. No choice about that for the molar mass. So we would like to use our liters in grams per liter, and we're using bar for the pressure, and so the actual value of R 0.08314 litre bar per mole Kelvin. So punch all that in and we get 1.11 grams per litre. Toughest thing here is knowing all of these values of R. Now what we could have done is we could have converted bars to atmospheres, and then atmospheres and litres would have been 0.0821 litre atmospheres per mole Kelvin. If you'd wanted to, you could have converted bar to pascals and then got the volume in cubic decimeters, but then that would have been grams per cubic decimeter, which is a little bit tough to do. Just watch out for all of the different values of R and make sure you use the right one. 250 mils liquid nitrogen. I give you the density as vaporized. What volume does the resulting gas? So we start with liquid and then it all vaporizes to the gas. So the first thing is we know the temperature and pressure. We want the volume. So we need the number of moles. Well, the number of moles is not given to us as a gas. The number of moles is ultimately given to us as a liquid. Okay, so the density of any liquid is mass over volume. We know our density, 0.807 grams per mil. Mass we don't know, but we do know that that unknown mass is in 250 milliliters. So the mass of nitrogen, just multiply this out, 0.807 times 250, 201.75. Convert that, of course, to moles. So now we got the number of moles of our nitrogen that started as a liquid, but then all became a gas. So now pop it into PV equals nRT. We know the pressure, 5 atmospheres, volume we've been asked for, moles 721, temperature 298, pressure in atmospheres, so the unit that we know for, or the value for R we know for atmospheres, 0.0821, so that's going to give us the volume in liters. Punch it out, and the volume 3 is 35.3 liters, 35.3 cubic decimeters. So question 13, what's the molar mass of a gas? Well, I said earlier that if we take the ideal gas law, PV equals nRT, and instead of N, we put grams over molar mass. Now we've got an equation that we can rearrange. And again, all those rearrangements done in the movie. In this case, I'm not going to rearrange yet. I'm going to throw in the values. So let's see what we got. Pressure, we're told 1.0135 bar. Volume 4.48 liters. Temperature 273 grams. 15. Pop all that in. Think about what value of R we're going to use. Well, we got bar and we've got liters, so therefore 0.08314 liters bars over mole Kelvin. Multiply all that out as appropriate and we get the molar mass is 75 grams. Same type of question, mass 560 mils, so we got volume, we got temperature, we got pressure, we got grams. Which of the following gases could it be? Well, again, PV equals GRT over molar mass. So in order to identify which gas, we'll find the molar mass. So pop everything in, pressure 1 atmospheres, volume 0.56 liters or cubic decimeters, temperature 273, and grams 1.1 grams. Put all that in, rearrange it, and the molar mass is 44 grams per mole. And of course, all the choices of gases, well, chlorine is 71, SO2 is 64, O2 is 32, CO2 is 44, CH4 is 16, so therefore it will be CO2. Grams, volume, temperature, pressure, get the molar mass, same equation. Converting the liters or milliliters to liters, converting, of course, Celsius to Kelvin. Pop it in, write value of R, 0.08314 liters bar over mole Kelvin. Again, you could have converted the bar to atmospheres. You could have converted the bar to pascals. You could have converted the temperature to cubic meters. All kinds of things you could have done depending on which values of R you know. I happen to know that liters and bar is 0.08314, so I use that. Multiply it through. molar mass 55.1 grams per mole.